So I am from Berlin, but I'm not German. I'm American. I've lived there for a couple years now. I write software for a living, and as you've already heard, my name is Devon. That's sort of all the interesting stuff about me. If you want to know more, I'm on the internet. And today we're here to talk about refactoring. So refactoring is one of my favorite things to do with code, actually. I love refactoring. It makes me feel good inside. But there are probably some people in the audience that may not know exactly what refactoring is. So let's get a definition out of the way. So this is Martin Fowler. Martin Fowler literally wrote the book on refactoring. He wrote the book in an object-oriented context, but refactoring, this is his definition. It's a pretty simple definition. I actually have a slightly more general definition. For me, anytime I am changing my code without changing my tests, that's refactoring. I think anytime I'm changing the source code without changing the visible behavior of my application, that's refactoring. It's doing the same thing, just in a different way. Now, you might be thinking to yourself, Devon, why would you change your code without adding a new feature or fixing a bug? What's the point? Isn't that a waste? But it's not a waste. There are valid reasons to refactor. One of them, one of my favorites, is to increase the ability to read or understand your code, to comprehend it as a human. Source code communicates to two different places. It communicates to the computer to tell it what to do, but it also communicates to other readers of your code, other people that might have to maintain it in the future, including yourself in the future. If you're anything like me, if I wrote code 6 months ago and I have to look at it again, it might as well be the first time I've ever seen it. So being able to read and understand code is very important and a good reason to refactor. People also refactor to make your code easier to change. Now, this is something that is a big thing in the object-oriented world where there are complicated design patterns and things. It's something we don't have to think that much about in Elixir because as a functional language, there's very loose coupling between elements and between objects, between functions, I shouldn't even say objects, but between things. So having to refactor your code to make it easier to change isn't that much of a reason to refactor in Elixir, but it is still something. You also refactor to lower complexity. So again, if you're anything like me, sometimes at the end of the day, you're working on a feature and you can't think of that really good way to do it, so you just do whatever comes into your head and you make your test pass and you're fine, and then the next morning in the shower, you're not thinking about anything and like the really elegant implementation just pops into your head so that you can go back into work and you can refactor your code to utilize that new, better, simpler, easier to understand implementation. And then you can also refactor to increase performance. Now this one comes with an asterisk because some people don't think that that is refactoring. By decreasing, for example, a page load from 5 seconds to 1 second, you're changing the visible behavior of your application. But to me, you haven't changed the correctness of your application. When I refactor for performance, I'm not changing my tests. So to me, that's still refactoring. I understand that for some folks, that doesn't really fit, but it's something we're going to talk about in our discussion today of why we would refactor and in comparing different refactorings that we're going to do. And also in today, because having to refactor to change your code isn't necessarily as important in Elixir or in other functional languages, we're just going to ignore that. So these are going to be the 3 things that we're going to look at today when we're evaluating these refactorings that we're going to do. Now, in general, all of these things are around trying to make code better. But better, I think, always has to come with a quantification. You can't just say something is better because it is. You have to be able to measure it, and you have to be able to compare ways in which something is better. And frequently, there are trade-offs that we have to make. So we're going to go on a journey today, all of us together. We are going to explore some implementations of some toy problems on a site called EXERCISM.io. And on that site, there are these toy problems that everyone can solve, and it's a really, really wonderful thing to look at when you're looking at things in a refactoring way. And again, for those of you that may not be familiar with EXERCISM, this is a sort of brief definition of what EXERCISM is, and that's Katrina Owen, who started the project several years ago. She's really well known in the Ruby and Go communities and is a wonderful maintainer of open source. Now, EXERCISM is particularly good for looking at what we're doing today, I think, because these numbers you see on the right are all of the numbers of different implementations of some of these little toy problems. Some people might call them katas or exercises, hence the name EXERCISM. That's sort of the joke there. But nowhere else, to my knowledge, can you see hundreds or thousands of different implementations of the same problem. It's really beneficial to read other people's source code, but frequently, for me at least, when I'm reading someone else's source code, a good half of the time, if not more, is spent just understanding the problem that they're solving, understanding the domain, and not necessarily seeing how they're solving it, being able to compare that to other solutions to the same problem. Now, for me, this is a really, really interesting way to collect some data and to see how people are solving different problems in the same way. So we're going to go through some of these problems, and we'll start with a very important one, binary search. It's important because it's on all of our tech interviews, and we all have to whiteboard to get a job, right? Like that's the only time you're ever going to use it. But we're going to look at an implementation today, a couple implementations, and we'll do some refactoring. So for those of you that aren't familiar with binary search, we'll go over sort of what it is quickly. So this is as big as my code is going to be. If you're having trouble reading it, way in the back, there are seats up front if you want to come up. So binary search is a recursive search algorithm. So basically what we have here is we have our search function, and it takes some items. In the case of this particular implementation, those items are a tuple of integers. And then we have a value that we're looking for. And because it's recursive, we're going to have to do some sort of recursing. And we're going to define a new private function, search arity for. And the way binary search basically works is every time you recurse, you take the element in the middle. It's a sorted collection. So you take the element in the middle, and you compare that element in the middle to the thing you're looking for. And if that element in the middle is bigger than the element you're looking for, then you know you can recurse again, but this time only caring about the bottom half of that collection. Likewise, if the element in the middle is smaller than the thing you're looking for, you can recurse again, but you know that you only have to care about what's in the top half of the collection. So each time you're going through the search, you're having your search area, and that's what makes it a particularly fast search algorithm for any sorted collection. So you see here, we need to first define our beginning. So that's the very bottom and the very top, and that's our search area. And then we need to find that middle index and that middle element so that we can compare that middle element to the value we're searching for. And then we have a con statement. And because this is a recursive algorithm, we need some base cases to end that recursion. So if the bottom index is greater than the top index that we're looking at, we know that the element that we're looking at is not in that collection. So we can return that not found atom. Likewise, if the middle element equals the value, congratulations. You've found your index, which is what we're looking for in this case, so we can return that tuple with OK and the middle index. And then we have our recursion cases. So again, if the middle element is less than the value we're searching for, we search again, this time only caring about what's in the top half. And otherwise, we can search again, only caring about what's in the bottom half. So that's binary search. And this is a pretty simple implementation. I like this implementation, but there's one quick way I think we can make it better. Whitespace. Whitespace is your friend. Elixir has a lot of flexibility with their use of whitespace. We can use whitespace to increase comprehension, and for me, this makes it a lot easier to comprehend. Your mileage may vary, of course, but whitespace is a good thing. Now, there's another way we can implement this exact same algorithm in a way that some people might consider a little bit more idiomatic Elixir, leveraging some of the things that are unique to Elixir and powerful in Elixir. So let's look at that refactoring. So we start with the same beginning, the same search arity 2, and then we define that search arity 4. It's the exact same as before. But now, as you've seen in that third line in that new function, we're replacing that con statement with a new function. And we're pretty much replacing a con statement with pattern matching and with guard clauses. And we can go through, again, that's our first base case. If we found the element, we can return that tuple. If the bottom is greater than the top, we can just return that atom. And then same thing here. We can either just look at the top half or the bottom half of the collection as we recurse. And you know what? If we're going to go this route to be consistent, we might as well do this too, right? We might as well just pull looking for that middle index and that middle element out into their own functions too. Now, this is a different implementation, very similar, same algorithm, just a different implementation. And there are pros and cons to these implementations. Because I like to have numbers for things, we're going to benchmark these just to see what happens, these two implementations. And to do those benchmarkings today, we're going to use a tool called Benchy, written by another Berliner, Tobias Pfeiffer. It's a wonderful tool. I encourage you all to use it if you need it for your benchmarking needs. And I'm just going to show you one example of these benchmarks, just so you have an idea of what they look like. We're not going to look at the other benchmarks as well. If you want to see those later, all the code will be on GitHub. But basically, to do these benchmarks, we define a function, and that function is going to accept a module. Because we have those two implementations defined in two different modules, we can pass them into this function. And then we're going to do some searching, and we'll see how many times it can do this in a given amount of time. And then the actual setup for the benchmark looks like that. You just give it a map with the things you're going to benchmark, and you see we use that, that bench func, and we pass in the modules that we've defined. And then we're going to run each function for 10 seconds each, which is a nice long time to benchmark. There's also some warm-up in there, so that's taken into account. And then here's what we get. So I'll be honest, this surprised me, because when I came to Elixir, I heard pattern matching is fast. Use pattern matching. It's one of the great things about Elixir. But functionally, it's kind of the same speed as a const statement. That's a big surprise to me, and it might be to some of you as well. And now, because I like to make charts and graphs to keep my head together, we're going to do that. We're going to run down the pros and cons of each implementation and see if we can find one that's right for us. So for readability, I prefer the const statement. Having those 4 cases next to each other helps me understand the algorithm a little bit better. For complexity, it's the same algorithm. It isn't that hard to understand. It's the same implementation. So to me, that's even, and for performance, that's pretty much even as well. But when we take a step back and we view our implementations across multiple things to try and have a holistic comparison of these 2 implementations, these 2 refactorings of the same problem, that helps us define something that is a little better, rather than just, for example, for me, readability is very important. So I have a tendency to overcompensate for things that are readable, but things that might be a little bit more complex, or things that might be a little less performant. So I encourage you to take a holistic view of what you're doing when you're refactoring. So let's look at another pretty simple one. This one's even simpler than binary search. So this one's called space age. And in this, you need to define a function that accepts a number of seconds to say how long you've been alive, and you need to tell how many years old someone would be on all of the planets in our solar system. So because each planet takes a little bit longer or shorter to go around the sun, the year lengths are a little different. So if you're 10,000 seconds old on Earth, you have more years than if you were living on Jupiter. So here's again a basic implementation. So we have a little map that's functioning like a lookup for us. And those numbers there are coefficients to tell us how relative the year is to an Earth year. So Earth is 1, and then everything else is relative to Earth. And then we do a little bit of math. So we take the seconds, and then we do our coefficient lookup with that magic number there. And this is pretty simple. This isn't bad. But I think we can do one better. A couple things better, actually. The first thing we can do is to give a name to that magic number. A very important reason to refactor is to name things, to name concepts that become clear in your code as you're developing them. Sometimes up front, we don't know all of the things that we're going to be dealing with. And as we work with our code, we develop a deeper understanding of the domain that we're working in and the problems we're trying to solve. And refactoring to name those concepts is very helpful. And while we're naming things and pulling out things that are constant into module attributes, let's pull that map out as well, and we'll name that something better than just lookup, something a little bit more descriptive. And now this isn't bad. We've done 2 good refactorings to name 2 concepts that were previously in our code but weren't named very well. But there's another way to essentially look up a value based on a given key. And it's a little tricky. It doesn't feel natural for someone like me who came from Ruby. It feels a little strange. Can anyone guess what that might be? It's pattern matching. So this functions exactly the same way. We're looking up a value based on a given atom. But there's some benefits to this. So when we benchmark, we see that the map lookup is almost twice as slow as the pattern matching. Again, this was a huge surprise to me, coming from Ruby, where a hash lookup is just about one of the fastest operations you can do to see how optimized pattern matching is in this case, and comparatively how slow looking something up in a map is. That was a revelation to me. That's going to change how I write Elixir code in the future. But I think we can actually do ourselves one better. So all of that math that was done in the body of those functions, we can use macros to basically do that math once at compile time. And now, we're still readable, we still see what's going on, but we're getting another little performance boost. It's a very small difference that has a significant input. That's the whole deal of refactoring. Small little things that are too small to matter, but they all add up to be significantly effective. And now when we benchmark these, that's another significant little performance benefit. So now we have an implementation that's twice as fast as a lookup in a map. And the other thing that really jumped out at me as a lesson that I learned from this exercise was to look for things that are constant and to try and avoid unnecessary computation. I mean, that's just a great rule in general. But to use the compiler to help you deal with things that are constant in a more performant manner. So let's look at our chart. So for readability, I think they're all about the same. It's a very simple algorithm. It's a very readable and understandable thing. Complexity, again, it's just about the same, but the difference here is in performance. That macro version is significantly faster, like with no other real trade-offs. So this is a rare case of where something is just better, in my opinion. And now I'm going to have some water, and while I do that, you can look at Chiba's. Okay, next one. This is a problem called allergies. The gist of this problem is that you take an allergy test, and the results of that allergy test come back as a number. And that number will tell you what you're allergic to. So if your score is 1, then you're allergic to, for example, eggs. If your score is 2, you're allergic to peanuts. If your score is 3, then you're allergic to eggs and peanuts. So let's look at an implementation a little bit further. So first we need to be able to say, am I allergic to a given thing? So you give the number and then the thing that you're looking for, and you're seeing if the item that we're looking for is in a list of the flags. But we need to make that list. And here's how we can do that. So we take the flags, and I'm sure some of you may have seen, looking at those numbers, those are binary numbers. We can use binary to see basically if a bit is turned on or off, and that can help us tell us what we're allergic to. So we use the integer digits with that 2 to give us the digits in a binary representation. And then we reverse it because, of course, the map that we have there is in human readable order from lowest to highest, but in binary it's reversed. So we need to reverse those digits to map up with the map because we're going to zip them together. And then we do reduce. We use a nice anonymous function with the multiple function heads to pattern match there. And if the bit is turned on, if we have a 1, then we know we can add that allergy to our accumulator. Otherwise, we just move on. And now that's pretty good. I'm generally pretty happy with this. I would push that code to production. But we can do a little better, I think. So we're going to keep this map the same. And we're going to keep this function the same, too. I actually really like this function. I think it's really descriptive. It tells us what's going on. It reads pretty much in English, which, as a native English speaker, makes me happy. But here's where we start changing things. So that list function, we can also do a filter map. That's built into the standard library. But the advantage, I think, here is we get to name another idea. We have that flagged A, flagged question mark. I say flagged A because it's fun to make fun of Canadians. So we have that flagged A function, and that will filter just the ones that are flagged, and then we can reduce based on what we have back from the filtering. And now that flagged A function, this is where things get a little tricky. This is the trade-off we're making. We've named another concept, and this will probably be faster, but who knows what those 3 ampersands are doing? Yeah, not a ton of people. So I know, again, for me, coming from Ruby, it's a pretty high level of abstraction, and very rarely do we need to think on a bitwise level. But that's a bitwise operator, as you see from that use statement up top. What that's doing is a bitwise AND. So it's comparing 2 integers and comparing each bit in those integers. And if they're both turned on, then it will be it will pass through as true. So 1 and 1 is true, 1 and 0 is false, 0 and 0 is false. And that's what's happening there. Now, we have the trade-off of using a slightly more low-level function, but we've also given it a descriptive name. So in my book, that's a win, because if you're touching this code again, you may not even have to know what those 3 ampersands are, because you know what the function's doing, because we've given it a good descriptive name. But I think we can do one better still, or maybe better, different at least. So we start again, and again, because I like that function, we're going to keep it. But now, we're going to do a little recursing. And before I continue, I'm going to tell you in advance that what we're doing is a reduce function. It's just reduce. Now, who knows what those lower than, less than, greater than thing around the flags do? Again, that's turning stuff into a binary. So a binary representation because we have those binary numbers. And now we can pattern match on that binary. So if the first bit's turned on, we're allergic to cats. If the second bit's turned on, we're allergic to pollen. If the rest of them are turned on, or if the third bit's turned on, we're allergic to chocolate, and so on down the line. And then, of course, we have our base case. Now, who here can read this? This is sort of what my mind looks like, or feels like, anytime I need to deal with binary pattern matching. It gets me really confused, because it's a little tricky to comprehend and to parse visually. But now, who can see the pattern? So the first we have 1, 7, and then we have 1, 1, 6, and then 2, 1, 5, all the way down the line. It becomes a little bit more clear when you mess around with some colors and some shading to see the pattern there. It's a little hard to see that pattern normally. But there is a reason to do this. It's really fast. Again, pattern matching is really fast. I again, was not expecting this level of difference between, I thought when I saw the bit shifting implementation, that would be just about as fast as it gets with the bitwise implementation, because that's a very, very fast operation. But because there are other parts in that algorithm, and because there are other things that we need to do, it's a little slower than this pattern matching. The pattern matching is actually a very simple algorithm. It's just a little dense to read. So let's compare. Now for readability, I really like the bit shifting version. I like that we've named the extra concepts. I like that it's a shorter implementation. Sometimes that's a lot easier to deal with. Complexity, I also agree that the bit shifting one is a little less complex. There are fewer operations that we're doing. It's a little easier to understand. But for performance, that's the big difference. If you have done some profiling and you found that this is a hot path in your code and this is something that you're spending a lot of time on, you might need to make that trade-off of readability and complexity for performance. That's a very, very common trade-off that we have to make. But I think it's important to know the trade-offs that you're making and the extent to which you need to make that trade-off. That's why benchmarking and profiling is very important. But really, what's the point of all that we've gone over today? We've seen that white space is your friend, that pattern matching is fast, that bitwise operators can do cool things. But there's another thing that I saw in going through all of these exercises in EXERCISM.io. And I think there's one general reason that people make less than optimal decisions. And I don't want to say bad decisions, because I don't really think there's a bad decision. It's all about trade-offs. But sometimes there are easy wins that we can do that people don't make. And I was thinking, why? Why would they do that? Why would they write something that's a little slower when you can just as easily write something that's faster? And I think there's one reason that this happens. And to illustrate this, this is where this talk takes a kind of strange left turn. And I'm going to need two helpers to come up. So Ole and Milad, come on up, and we're going to do sort of a little play for you guys. So in this example, Ole, if you want to stand here, and Milad, stand over here. In this example, Ole and I are on a team together, and we're working on our stuff individually, and he has something that he needs to do to the code. And depending on what he chooses, there may be consequences to those decisions. Okay? So again, right? So depending on the hand that Ole picks, there may be consequences. He needs to get this nice shiny euro. That's his job is to find this euro, and it's going to be in one of my two hands, so he has a 50-50 chance of finding the euro. But he has a decision to make, left hand or right hand. So, Ole, which hand would you choose?
That one.
Nope. Okay. So, let's try again. Which hand?
Same.
Nope. Let's try again.
We keep this going.
50-50. It can't go on that long. Okay. Try again.
Other one.
There you go. Now, because Ole chose the right hand, Milad punched me. That caused me pain. But he didn't know, did you? You didn't know that was going to happen. Yeah. Now that you know, by choosing the right hand, that's going to cause me pain, would you ever choose the right hand again?
Do I get the euro?
Yes. You do get the euro. No, the euro is worse. Thank you for helping. So that's the little weird thing. Milad, Ole, thank you very much. Let's give them a hand for helping. So, in general, people make the best decisions they can with the knowledge available to them at the time. Now, this is actually a really well-known problem in economics. It's a problem called the imperfect information or the imperfect knowledge problem. And it basically means that if someone doesn't have all of the knowledge they need in order to make a decision of the benefits and the consequences of that decision, that it's impossible for them to actually make the best decision. And the way to solve this is by sharing more information. And a particularly great field, part of economics, I think, is a field of study called behavioral economics. And that field of study was pretty much started by a man named Richard Thaler. And wouldn't you know it, he's written a book, well, co-written a book with Cass Sunstein. Now, in this book, as you can see, they talk about nudges. And the way they define a nudge is it's anything you can do that will influence someone's decisions. We, as software engineers, have a lot of power to influence people's decisions, both in the design of our applications, but also in the choices we make when we code. We can influence our decisions in the future. We can influence our coworkers' decisions. We can have a lot of influence. I think it's time that we do a little bit more nudging. So, the first thing is to lead by example. If there are any of you in the room who happen to be maintainers or contributors to any popular languages or frameworks, I know when I have a question about how to do something in Elixir the right way, the first place I go is to the Elixir source code, or to the Phoenix source code, or to the Credo source code, or the Benchy source code. Code written by people I think are doing good things, people I respect. And that's how we propagate ideas throughout a community. We lead by example. If we do something, if you happen to be in a position of influence, your decisions will have impact in the rest of the community. So keeping that in mind is very important. When you're trying to ship a bug fix late at night and you think, oh, I'll just do this hacky little workaround and it'll be fine. Yeah, it will probably be fine, but it could also influence the way that we all write code. And that also matters within your teams. If you have junior developers on your team or people that are new to Elixir even, the way that some people may design or write code is going to influence the rest of your team's behavior. So lead by example. It's a very important thing to do. Also, talk more about your mistakes. We all like to talk about our successes because that makes us feel good, but it's great to learn from other people's mistakes. There's no reason that we all have to keep making the same mistakes over and over as a community. When one person makes a mistake and learns that this is maybe not a great way to do something, you can share that knowledge with the rest of the community, and then we all don't have to keep bumping our head up against the same wall. Now, because I'm putting my money where my mouth is, starting today, there's a new repo on GitHub called Fast Elixir on my GitHub. So I, as I mentioned, came from the Ruby community, and in Ruby, there's a very similar thing called Fast Ruby, which shares some common idioms in Ruby and shows you some benchmarks to show which is faster or slower. Lots of those, before I had seen them, I never knew. I never knew which one was faster or slower, and after you see it, you don't make that mistake again. So I would like all of us as a community to start sharing that information. There are 2 examples up right now that we've actually seen today. Well, one that we've seen today, one that about I/O lists and how they're faster than string concatenation, which for all of you Phoenix folks, that's where a lot of your speed comes from. So if all of you who have far more production experience with Elixir than I do, hopefully, have things to share, this is a place that it would be great to share them. Pull requests are very much accepted and welcome. And then the last thing is more and better tooling. One of the reasons that I was so excited about coming to Elixir was because tooling was at the center of the language. And I believe that tooling is a very important part of a language. But I think we can do a little bit better. We have more road to go down. Now, some of you may have noticed that I played a little trick on y'all with some of the code examples. We have seen 4 different but completely valid ways of defining a function. And we have seen 3 different but completely valid ways of using the pipeline operator. And those are just the beginning of the ways in which I was extremely inconsistent. Trust me, that was by design. I was not just being lazy. Part of that came out of me trying to think of the one right way to format these slides. And I decided to just say, forget it, and go a totally different way. And I did some research over the last couple months about formatting. And I found this study, which is one of the better studies that I had found by 2 researchers at the University of Oregon. And it's kind of an old study. It goes back to 1991. But it made me think that maybe formatting doesn't matter. Maybe all of those discussions that we have are not the best use of our time. Now, I like to prefix some of my more controversial ideas with this. I like to think of it as like the MIT license of ideas. But don't make me think about formatting. It's 2017. There are more important things that we can spend our mental cycles thinking about, more important problems to solve. Just let a tool do it for me. And then I was actually really happy to see this in this morning's keynote. So I'm happy that it looks like this tool might come into existence, hopefully. But there is a good amount more that we can do in tooling as well. I'm a big fan of some of the tooling that we have, and I think we can do more. Credo is a wonderful project. I think we can do a lot with that, and it's done in a very empathetic and kind way, which is a great difference from some of the other static checkers out there. But yeah, tooling is something that I think we can do better at. We also need a definition of complexity that works. You may notice, of the 3 things that we looked at, if we remove formatting as a thing to care about, and then we can benchmark performance, then the only thing that we need a number for is complexity. And complexity is really difficult to understand in functional programming, because really all we have is the ABC complexity or the cyclomatic complexity of a given function, because that's our unit. But in Elixir especially, I think that's not exactly an accurate representation of complexity. When you have pattern matching and you have 10 clauses, that's syntactically, or that's semantically the same thing as a case statement. It's a tough problem to solve, but I'm confident that we as a community can solve it and have something at least, some baseline that we can use as a solid measure. So that's sort of the end of the rant about that part of the talk. So that's it for me today. If you're wondering why I put so many Shibas in my slides, that's my Shiba, Miki, when she was a little puppy. She's much bigger now, but she does still like to lick my beard for some reason. So that's it for me today. Let's have some questions.
So does anyone have any questions?
Hi. Thank you for the talk. Just out of curiosity, have you tried refactoring the last version, the binary pattern matching version of the ALLERGIES examples, and make it and use macros to make it readable but just as fast at compile time, and does it work?
I haven't. That is something that I thought of doing, and actually I was speaking with someone last night, and apparently there is an existing library that kind of does that they had fooled around with. I forget the name of it, but that was another thing that I think, the binary pattern matching is one of, I think, the stronger features in Elixir, to be able to pattern match at that level, but it's also one of the biggest, it's one of the hardest things in the language to read. So some sort of macro that would encompass all of that behavior would be incredible. I mean, I would love to see more of that. It's something that I would love to dive a little bit deeper into, because I think as a language we could maybe have a more user-friendly API for that, like a more user-friendly way of defining those. But no, I hadn't tried that. It's something I thought about, but didn't really have time for this.
Thanks. Yeah, that was a good question, and thanks to EasyMail for sponsoring again. Does anyone else have a question? If you just raise your hand, I can pop over. Going once. Cool. Going twice. All right. Last chance. Well, thanks so much, Devon.